I wanted to work a couple more examples so that you could see that when you're in the context of these improper integrals, if you do have to determine, once you determine convergence or divergence, if you determine that your area does converge to a value and they ask you to what value does it converge, you will be able to determine what value that this improper integral converges to. So let's just do this example really quickly. I wanted you to be able to see that we definitely can do something like this. Not a problem. So from 1 up to b, I'll write this as x to the negative 1.01 dx. So we're going to have the limit as b approaches infinity. The antiderivative here is 1 over negative 1.01 plus 1, x to the negative 1.01 plus 1. And we're integrating from 1 to b. So we have the limit as b approaches infinity. This cleans up to 1 over negative 0.01 x to the negative 0.01 from 1 up to b. So we'll have the limit as b approaches infinity of b to the negative 0.01 over negative 0.01 minus negative 1 over positive now 0.01. I used this negative here to make that positive. Hopefully you can see that. And then the numerator is going to be positive 1 to the negative 0.01. So let's see what's happening here. We can rewrite this term with a positive exponent on b, and that may help us recognize, we'll put the negative in the numerator. That should help us realize, and 1 to the negative 0.01 is still 1. Hopefully you realize that. So as b goes toward infinity, this term goes toward 0. So this is 1 over 1/100th. This area is converging to 100. So don't obsess or worry about, am I going to be able to find the exact value this converges to? Yes, if that is the question that is asked, you are going to be able to find the antiderivative and determine to what value that improper integral converges. One final example. I haven't worked an example yet where both limits are infinity. Here, the lower limit of integration is negative infinity, and the upper limit of integration is positive infinity. So I want to remind you that if we have this case, we always work from left to right. A is less than b, which is less than c. If I want the total accumulated area from a up to c under any function, it is true that I can break that interval up over any interior horizontal value and add those two separate areas together to get the total area. That is a property of the definite integral that we learned last fall. So we're going to use that on this problem here. We are going to, and I'll rewrite my integrand like so, we are going to split the interval from negative infinity to positive infinity over some interior point that we are guaranteed lies in the plane between negative and positive infinity. We can pick any value we want to, any real number value. Why don't we pick something easy like 0? And we're guaranteed that this is equivalent to that area. They will be the same because we're just using properties of the definite integral. So I'm going to bring limit notation here, and I think I'll go ahead and go directly to my antiderivative function. You can see that this is a u substitution. So this is negative 1/2 the integral of e to the u du, which is negative 1/2 e to the u plus c. For us, u was negative 2x. So I'm going to go ahead and just write my antiderivative function here. And I am integrating from a up to 0. I'm going to add to that, as I take b toward positive infinity, the integral from 0 up to b. So let's plug in and do fundamental theorem. The limit as a approaches negative infinity is negative 1/2 e to the 0. It's plugging in this upper limit minus negative 1/2 e to the negative 2a. So there's the first part. I'm going to add to that the limit as b approaches infinity of negative 1/2 e to the negative 2b minus negative 1/2 e to the 0. So now let's take a to negative infinity. Still need the limit notation. Still have variables there. Negative 1/2 times e to the 0 is negative 1/2 times 1. Plus, I'm going to, well, I think maybe I'll just put in negative 2 times negative huge. How will that work? Hopefully everyone can see that. We'll just use huge here. It's not going to hurt anything. And we'll plug in positive huge for b plus 1/2 again times 1 is 1/2. So there we are. So let's look at this. This is negative 1/2 plus, this is e to the positive huge. Do you see that? Negative 2 times negative huge is going to give me positive 2 huge. That's huge. We can, in this context, since we're talking about the answer, we could write that as infinity. Then we're going to add to that, technically I guess subtract because this is a negative value, negative 1/2 e to the negative 2 huge is the same as 1 over e to the huge. That term is going to 0. So let me get my 1/2 out of there. This whole term is headed toward 0 when b is headed toward positive infinity. And then I have plus 1/2, just copying that down. This area diverges. So there you have it. There's a little bit more information on improper integrals, specifically where we have infinite input values and interval over which we are integrating. That should give you some idea of how to deal with these improper integrals. Please watch your notation very closely. Come to class next time. We'll work some homework problems.